So, honorable judges and worship opponents, this is Team TYPT, and I'm going to report problem number 9, magnetic assist. This is the problem statement. Attach one or two magnets to a non-magnetic and non-conductive base such that they attract the magnet suspended from the string. Investigate how the motion of moving magnet depends on relevant parameters. This is the phenomenon here, and we are now going to focus in on the direct trajectory of the pendulum and the application of energy, relevant parameters, and whether it attract or repel will that affect. Here are some observations and further consideration. For the part of further consideration, we consider the position of magnets, attracting or repelling, the initial position of the pendulum, and the number of magnets. As for the absorption part, the magnet ultimately converges, but that does not mean that the final velocity is zero. And the second part, even released from the same position, the outcome varies, which means that it is highly sensitive to the initial condition. The third part, the magnet follows a certain pattern and enters an irregular motion. This is the phenomenon. We can see that when the magnet is attracted by the base magnet, it actually vibrates upon the magnets on the base. Here is the coordinate used in all the later presentation. So since the starting point is difficult to control, we will design and present a mechanical releaser, and that to make sure all the experiments are conducted in a scale of 10 repeated times to examine its most likely motion. This is our coordinate elaboration. Here we introduce the following symbols to later deviation and calculation. For the background information, because in our experimental setup, R is far more bigger than L. So we can, by referring to this paper, we can say that the magnetic field can be denoted as this equation. So calculating the negative dot product of a magnetic dipole moment and the external magnetic field, potential energy of a magnetic dipole can be derived as shown in equation 2, this equation. And we substitute and rearrange. We get equation 3. And here, the n is equals to 1 or 2. As for equation 4, we calculate the power of energy loss caused by air resistance. And the conclusion is that the velocity vector and the air resistance vector are parallel to each other, which means is under the windless condition. And the speed of the pendulum relative to the wind speed is simply the motion speed of the pendulum. So generally, magnetic dipole and gravitational forces are considered conservative force. Also notice that tension force does no work in this sense for the following reasons. If the string is vertical to the magnets, it does no work, it's obviously. If not, it means that the string isn't taut, and it also does no work. So we can have this equation of energy conservation where the kinetic energy and its potential energy will be a constant, which equals to the initial potential energy. So when the magnets are attracting to each other, as long as the following conditions are met, the magnets will be attracted, where the work done by the magnetic potential energy is bigger than the kinetic energy, which means the kinetic energy cannot overcome the work done by the magnetic potential energy. So we will base on this equation to calculate the threshold speed that the suspended magnets will be attracted by the base magnets. So to further dive into the exact value of the minimum speed to conquer the magnetic potential energy, we rearrange the equation to get equation 7. So if the speed exceeds this threshold, the pendulum moves away from the magnets. So now, because like I mentioned before, it is highly sensitive to initial condition. So no matter how Earth's magnetic field is so small, we still need to consider it. So in equation 9, it explains the relationship between magnetic potential energy and magnetic force. So when the magnetic potential energy is small, the magnetic force is also small. Vice versa, it can be shown in equation 9. The magnetic force is shown in equation 10 after substitution. Here, A represents the base magnets and B represents the magnet that is suspended on the string. Here are our experimental setup. The base is fixed on the table and the magnet base magnet is fixed on this non-conducting and non-magnetic phase. And we use a correction Hall and releaser to accurate the initial conditions. This is our preliminary experiment. Here, in a repulsion equilibrium, we examine the magnetic dipole moment through changing the distance between two magnets. And these are the rags. And here we aim to find the dipole moment. So by applying the magnetic dipole moment formula for two thin round magnets, as shown in equation 9, and after using substitution in equation 10, we can get the equation in 11. So rearrange it, we get 12, and to determine m squared, the magnetic dipole moment squared, we use linear regression and set k such that mg equals to kn squared plus a constant. So here we consider the slope of the square root of the slope of this line to get the magnetic dipole moment to equals to this value. And here is experiment 1, the landing position. Here is a two magnet experiment. We launch a suspended magnet from different initial angle and radius in order to investigate the probability distribution of its landing position. And here we define length as the magnet slowly converge to a stationary magnet, which means that length here does not mean the final velocity is 0. Here are some independent variables and control variables. So this is our result. Here we provide a graph about the probability distribution of different launching positions. The closer the probability to 1 is, here, the black one, the higher possibility to land on the left magnet. So if it is white, it is high possibility to land on the right magnet. So although we have tried to be as precise as possible, some areas outside 5 centimeters here still exhibit possibly around 50%, and which means it's kind of random. The sensitivity to initial location in 90 degrees to 207 degrees in these directions is likely due to the little difference between two magnetic force of two adjacent base magnets, which is placed in these two places, so making the landing positions more elusive. On the other hand, because the difference is more distinct in the 0 and 100 degree direction, the landing is probably become more uniform. And in experiment 2, using the formation models, we will analyze the pendulum's energy transformation and investigate the respective relationship. Here, we aim to analyze the energy transmission during the pendulum-like motion and investigate the relationship between different parameters. Here are our control variables, and this is our results. We can see that the yellow line is the total energy, and which can be shown at these two graphs. One magnet attract, and one magnet repel. We can see that they converge to a horizontal line, which means that it can be applied to the energy conservation. And also in two magnet attract. So here are some possible deviations. The total energy remains constant, which implies that energy conservation is not affected by the number of magnets or the direction of the magnetic dipoles. And second, when kinetic energy reaches its maximum, the sum of gravitational potential energy and magnetic potential energy reaches their minimum. Because these three energy, the sum of these three energy is constant. And the third part, the slight nutation possibly originates from the vibration of the string, which I mentioned in the previous presentation, when the suspended magnet is close to the base magnets. So in experiment 3, we here want to observe the similarities of pendulum trajectory under different parameters. Here are some independence variables and control variables. I provide a one magnet attract, and the position of the base magnet is as shown above. And this is the xt and yt graph. If we combine it together, we can get this xy graph, and we can see that it actually will eventually converge to one place. And here is one magnet but repelled, and also the position of the magnet is placed in 0. Here are also the xt graph and the yt graph. And also we consider the xy graph, and we can see that as long as it comes here, he will be repelled and shift back, come here and shift back. this distinct U-turn phenomenon occurs. And this is for the two magnets attract, and the position of the base magnet is shown as above. Here in time 1, we are not here, the mechanical is not yet released, so it is a horizontal line. And this is also the XY graph. We can see that the pendulum actually rotates around one magnet and then converges to another magnet. So in experiment 4, we aim to provide a quantitative result about the threshold speed, which can be derived from this equation. These are some independent variables and control variables. This is for the one magnet attract. Two magnet attract, and here is the calculation. We can see that we plug into this equation and we can get the threshold speed of the experiment is this value and the theoretical is this one, which we can have a small error about 1.81 only. And as for two magnet attracting, we can also get a 1.2 error. So here are some conclusions. We can obtain an instantaneous speed if the initial position and the instant position is provided through our series. And for the trajectory, attraction, they will rotate around, and for repulsion, the U-turns occur. And here are some possible deviation. The instant bend of the string may cause deviation to the system, like energy loss. And for future research, we also want to change the base into a conductive or magnetic base to investigate what will happen. And also, we would like to compare a stick-based pendulum to compare to the experiment here, a string-based pendulum, to see whether to prove that the tension force does not work. And here are some reference, and that's my presentation. Thank you.
Please turn to page 11.
Okay.
You say I want to tell you why kinetic energy decrease.
Why kinetic energy decrease?
Yes.
Because, kinetic?
You say it doesn't have enough kinetic energy.
Oh, because through the process, like, this means that when the pendulum goes down, the magnet on the base part will attract the magnets here, right?
Yeah.
So you will let it slow down. So if this forces between these two magnets is bigger than the kinetic energy here, so which means that the kinetic energy cannot provide enough energy to overcome the restriction.
Well, I mean the process is decreased.
The process is decreased.
The kinetic energy decreasing process.
The end. Can you?
How it decrease?
How it decrease? He actually is release it in an initial speed 0, but with an initial potential energy. So when it goes down, the kinetic energy increases. Like the potential energy turns into the kinetic energy.
Okay.
Right.
Okay. And page 7 or page 7. You said the L is far from the R.
Far smaller than R, where L means the thickness of the magnet.
But as I know, if the L far from the R, the R can see as a 0, can equal to 0, right?
Why? Like 1,000.
In simple harmonic motion, we learn the L if R is far from the L can be.
In simple harmonic motion, there doesn't exist an R. Here, R means distance between base and pendulum magnets.
What is thickness of the magnet?
The base magnets and the the distance between the base and the pendulum magnets.
And
you may.
okay, thanks.
Yep.
And it's So, please start. Okay, my name is Ben Daniel. I'm a opponent. I'm from Team Huayang A, and my school is National Zhanghua Senior High School. Problem statement: attach one or two magnets to a non-magnetic and non-conductive desk such that they attract magnet. Suspend from a string. Investigate how the motion of the moving magnet depends on relevant parameters. Next. And the reporter, I want to remind you, you have main diagram and logical expression, and I also have some suggestion to you. The diagram is too messy, and I think you can add the 3D diagram. And the third, the charts are confusing and hard to interpret. Okay, and I wanna save you some question. Okay, please turn to page 23.
Okay.
This picture is the possibility that the magnet will pass, right?
Will finally converge to that profile. Like I have placed two
It's
magnets.
the end position the magnet stop.
Yeah. So we placed
But
like.
I want to know which direction is you put the magnet.
Which direction?
In this, maybe you put the magnet from this direction or this direction, and which direction? You say it's the magnet start position. The possibility of the.
Oh, you mean like where did I initially release?
Yeah.
Like for example, in this part, like release here, and like in this part, he has like 0.6 to go to the left, right? So in this, it means that in 10 times, we can observe that it goes to this part 6 times and here 4 times. So we color this in this color.
Okay, and turn to page 27, please. How you calculate the energy?
By the formula as provided by
You don't use sensor.
sensor. Like how can you use sensor?
The sensor maybe can test on the magnet.
And then you want to track.
I mean, so you use the formula to calculate this energy. And do you consider the air resistance?
Yes.
But I don't see it in the.
Yeah, it's in page 9. This is the power of air resistance. Like if this is V squared, it is the force, and you multiply V, and we can see that in extreme conditions, the maximum of the air resistance is only this big. So compared to the graph we have.
You think it is small enough to ignore?
Yeah, like here you can see it's 10 to the power of -4.
So you say it is a very sensitive system.
So I mean,
Very sensitive.
So you can see some vibration here. Like ideal, the yellow line, symbolize the total energy. Supposed to be a horizontal line. straight forward. So there will be some oscillations between the lines, right? So this may be caused by the air force you mentioned, or like I mentioned before, when the pendulum comes inside the magnet. Suppose this is the base magnet here, and I come back here. Actually, the upper magnet suspended from the string will like tilt, tilt, which means that the tension force will not be vertical to the movement.
When it tilts, does the string
Yeah.
bend?
So there will be a lot of energy losses or gain. So the line will not be a perfectly horizontal line. Will be some oscillation there.
And how you think the trend of the yellow line is like which line in the picture? Which line's trend is the same as the yellow line's trend?
The sum of these
Is the
energy. Because the yellow line means the total energy.
Oh, okay. Turn to page 29, please.
You are curious about the energy transmissions between
the total will remain constant. Why it will not have any waste?
Yes, it has some waves. As shown in the graph here, you can see some vibration here. But ideally, it should be like a perfectly horizontal line. So, but in the real life condition, there won't be a perfect energy conservation. Like you cannot calculate all the energy losses. So, as long as the arrows between these, the highest and the lowest is not that big, I can assume that the energy conservation is still fit to this condition.
Okay. And you say have some loss. And can you say some example for me, such a what condition make the loss?
Okay, you can see in the third part, the slight annotation possibly originated from the vibration of the string, which means like this again. You come here, the upper magnets sometimes will tilt or spin, right?
Yeah.
So which means that the tension here will not vertical to the displacement of the magnets. Will cause some energy loss, like it will vibrate around here. I can show you some videos. And you can see that actually it will like this. And this vibration.
When it tilts, and the string will shake.
The string, the vibration, like it will be attracted.
So the energy loss is at a string.
Yeah, or also when you suspend it from the top part, here the friction here also impacts.
Okay. And please turn to page 35. Can you explain why?
The trajectory? Oh, yeah. Like I placed the magnets here, and here the 0, has a magnet, but that is repulsing to the upper magnet. So when this pad spins down, it will be repelled from this. So it will go up. And then to reach its highest point, it goes back again, right?
Okay.
And repel again.
And I want a comparison with 37.
37.
This is why is move way is so different?
Because this is attracting and two magnets.
Where is your two magnet put?
Here, 500 and minus 500.
5. This.
This is meters and this is centimeters. Sorry. Sorry.
So the different magnet put the different move way.
This is because this is attracting, so which means that it will be attracted except for being repelling. It will be attract, comes here, and eventually converge to these magnets.
Next page. 36. You say that we'll have a different move way. And I want to say if the magnets change the number of magnets, the x move away will, and the y axis move away will have some arbitrarily change. Will it change arbitrarily when the number of magnets is not changed?
You can first see this. This is a two magnets attracting a y, t, and x, t graph. And we also provide a one magnet repelling x, t. You can see this huge difference, right? You want both attracting. We also conduct one magnet attracting. So we can compare those different trajectories.
So you mean the one magnet, when at the one magnet, the axis move away will have a big range than the two magnets.
What did you mean by big?
Range.
No, it
The
actually.
axis range.
I would not say that because actually it's like this, like come back in this. So I don't know what the range you mean is.
We can turn to 35 and 36. I show you 34 and 36.
Oh, 34.
It means when it's one magnet, the axis biggest move away is at this point, and the lowest point is here. So it turns to 36.
36.
But in this picture, the axis will not have the so much gap.
I would not say that. I would not suggest you to compare in this situation because in this graph it's two magnets and also attracting. But in the previous one, it's one magnet but repelling. It's too many differences there. So I'm not sure whether you compare this picture in order to get one conclusion.
Okay, so you don't suggest me to show the trend, the axis move change comparison with the two different number of diagrams.
I think I do suggest you to compare this graph. This is a good idea, but not with two magnets attracting and one magnet repelling. Instead, you can compare with this is one magnet repelling. Never mind. You can compare it. You can compare one magnet repelling and one magnet attracting the trajectory. This will be more meaningful.
Okay.
And two magnets attracting, two magnets repelling. This will be better if you want to compare the trajectory.
Okay. So please turn to page 14. 40.
Oh, 40. Sorry.
And velocity is mean. Your velocity have direction.
This is
positive, negative.
Oh, this is track by traction. So we here aim to find the.
So now your velocity doesn't have.
I want to know the threshold. Like we can know that when we use tracker, we can know that when the upper magnet will be attracted and never goes away under the base magnet. So we can measure the velocity when it goes up.
Okay.
So we can compare it to the theoretical model here we provide, and we get a small error.
I mean, is the velocity have the direction? If I run this direction, I have a positive velocity.
That's my bad. I think that what I want to say
only,
here is only positive. Maybe I should change it to a speed.
Please summarize the discussion.
This picture, for example, the vertical axis is stand for the velocity, only for number not positive or negative, and the access range change the number of the magnet. Change the number of the magnet will change the move way, and the initially position is very important to this phenomena and the experiment. Thanks.
Okay, so thanks for the both of you. So first, I would like to, because the participant have stated motion, so first I will focus on the motion. So first is like you have mentioned, before I mentioned that the geomagnetism will have effects. However, you didn't show so how it affect the motion of the magnet.
Oh, we calculate.
Upon you think that the geomagnetism will also affect the motion as well.
The geomagnetic.
Like a magnetic field from Earth. Will it affect the motion?
Oh, I think it will because the Earth and the north and
Yeah, it will affect.
Well,
Okay.
it will
We
affect.
actually calculate here and we find that this.
So I think you can show the motion.
Oh yeah, I can show you.
Okay,
the
it's fine, fine. So next I would like to talk about like you have mentioned that the line will vibrate, right?
Oh, you mean the energy conservation?
So and did you consider the orientation of the magnet? Like
Orientation?
like the magnet will spin or the
Oh yeah.
near magnet. So,
So
there
there
are
is-
theory.
No, so there will be oscillations in the.
Yeah. So you should consider. So do you think that because the magnet will rotate,
Okay.
so do you think it will affect motion and
If it rotated, I think it
I see.
will.
yeah
I think it will
affect?
affect the.
Okay. So next I will like before I mentioned about the irregular motion. So what is the definition of irregular motion?
Oh, the definitions. It's just because it is highly in this example. Although it converged to one magnet because there's one
So
magnet.
is there any like quantitative definition of the?
What do you think about how do you define an irregular thing?
It's like
Can you provide me an example?
it's like you can like you have something can calculate to show
Show the.
like for it's fine, it's fine, yeah. And next I would like is there any equation of motion?
Equations of motion. No, we considered a energy distribution here. So if you want to derive the equation of motion, you can use the Lagrange and apply it to the Lagrange Euler
And next
equation.
I would like to because you have considered every system once. However, is there any damping force like the friction and but you didn't have considered. So did you think there is another damping force in the system? For example, like friction or
You said is that
air resistance? Yeah, it's like the air resistance.
Another damping force. I think
Is there
probably not.
Not okay. So I agree that I suggest that you should make a plain experiment so you can consider other damping forces.
So we consider its order of magnitude in order to testify our statement that we can neglect that.
Okay, fine. So last, I would like to ask also, what is the main cause will cause the motion of the magnet?
Will cause the motion of the magnet.
Like with
The interaction between the energy, potential energy, and the kinetic
No,
energy.
I mean like there in the during the parameter is the fixed distance to the two magnets.
Time is up.
The thing.
Fixed.
Yeah, time is up.
This one. I'm a reviewer from Team Maxwell, and today I will review the problem number 9, magnetic. So the main focus on this problem is the motion of the magnet, and the reporter also mentioned that the velocity of the magnet. And that is a summary of the report. For simple explanation, the simple focus on the magnetic potential energy and the air resistance and the considered magnetic force. And the experiment, they have mechanical releaser for the magnets. We can control the releasing of the magnet and the landing position and the energy of the magnet and trajectory of the magnet and speed of the magnet. And then the reporter strengths. They have mechanism release of the magnets and complete quantitative theory and did many experiments and consider many factors such as the air resistance. And the suggestions, they could extend more mechanical mechanism for releasing magnet factor. And they could talk more about the entire motion of a trajectory or trajectory, and could do more experiment about the trajectory and could explain the effect of the geomagnetism more, and could try to get the equation of motion, and no comparison between the theory and the experiments, and could provide definition of the irregular. And that is the summary of the opponent. The summary of opponent focus on the energy loss, which is the string is vibrating, and we think that, and also they focus on the velocity, which is also positive. So we think that the opponents could focus on more experience data, such as how they're releasing the magnets. And that is, and that is the, and the discussion between the opponent and reporter. So first, the opponent asked about the energy loss, and which I mentioned before is we say that due to the magnet vibrating and the string vibrating, so it will cause, and also the air resistance will cause the energy loss. And and we also agree with the reporter. And that is the extent of the trajectory. And first say the magnet attracts the magnets, which is the equilibrium point of the magnet. And that is what's the range of movement difference. And they say they give many different parameters. And there is no, like what I mentioned, there is all positive in the velocity, and there is the reporter's mistake. And that's the question I asked the reviewer, I asked the opponent and the reporter. So first I asked the effect of the geometry, and the report is, I mentioned that it is small, and we think they can explain more. For example, they can just show the chart to the trajectory of the magnet more clearly, and then the orientation of the magnet, because they have mentioned that it will vibrate, so the magnet will orientation of magnet as well. So they didn't consider in the theory, so I think they should consider it. And then the definition for irregular. They didn't have no quantitative or qualitative definition of the irregular. They just show that there is really mass trajectory of the magnet. And then the equation of motion, they didn't consider they didn't have the equation of motion. And that is the question that I asked about both of them. So first I asked are damping, because the reporter only consider the air resistance, but we think that there's also some actual friction. So we suggest that the reporter can do a blank experiment to make sure that all damp force have been considered. And that is And that's the main point in the discussion. So they didn't consider the complete motion of the pendulum, and they didn't discuss the orientation of magnets, which is maybe will cause the energy loss or the trajectory of magnets, and the equation of motion and the definition of irregular motion. Which I have affirmed that they maybe can give some definition, qualitative or quantitative of it. And then there's other different force, which is such as the force friction and the main cause of the motion, which means that maybe the fixed distance between the two magnets, the numbers of magnets, or the releasing height, or the releasing initial speed or initial points will affect the motion. So they didn't discuss the main causes which can affect the trajectory of the magnet. Thanks.
This is the reporting concluding the remarks. For the first point, clarification on possible energy loss. We think that the vibration may caused by the energy loss, and we think that it may caused by because it's sensitive to initial conditions, like the geomagnetism, the air forces, the reviewer mentioned. And as for the trajectory explanation, he also wants me to provide a definition for irregular. So I think maybe in my later experiment, or when I have massive database, I can calculate the lambda value to say that to prove this is a chaotic system, and also give you a definition about irregular. And also, we focus on kinetic and potential energy instead of motion. But if you want the motion of equation, you can instead use the Lagrangian and just apply it to the Euler-Lagrange equation to get the motion equation. But we did not include it. But that's what I can do later. And as for the blink experiment, the reviewer suggested that I can release it and without a base magnet, right? But the thing is that the air resistance, the air drag, has something to do with the velocity. So if the base is here, when the pendulum thing goes down, the velocity actually changes. So this will not, this will have arrows here. So instead of saying that instead of calculating it and say that there's error, I prefer to calculate the extreme conditions where I can say that the order of magnitude is extremely small, so that I can neglect the air drag to say that. And that's all my conclusion. Thank you.
So, question time for the jury.
I have a question for